Hey everyone, today we are going to deal with the topic generation of AC. What is a generator? A generator is an electrical machine which converts mechanical energy to electrical energy. Generator is a machine which converts mechanical energy to electrical energy. So what is the input to an generator? Input is mechanical energy. So input to an generator is mechanical rotation. The rotating part of the generator is rotated by using an prime mover. The prime mover may be water turbine which is driven by water stored in dam, or it may be an wind turbine driven by the wind velocity or anything. So what is the output of the generator? The output of the generator is electrical voltage. So generator is an electrical machine which converts mechanical energy to electrical energy. Input given to a generator is mechanical rotation and output of the generator is electrical voltage. So what is the principle of a generator? The generator works on the principle of electromagnetic induction. It works on the basis of Faraday's law of electromagnetic induction. So when a magnetic flux linking with an coil changes, voltage is produced. When a magnetic flux which is linking with the coil changes, voltage is produced or EMF is generated. And this induced EMF is dynamically induced EMF. Next we shall see the construction of a generator. A generator comprises of two parts. One is the stator. All the stationary parts in the generator together is called as stator. And the other is the rotor. All the rotating parts together is called as rotor. And the stator has three parts. One is the stator frame, another one is the stator core, and the next is the stator winding. The rotor has two parts. One is the rotor core, another one is the rotor poles or projected poles. Next we shall see the construction of a generator in detail. So in the screen we can see an symbol generator. It is not the practical generator. It is the symbol theoretical generator I am using for explaining the working principle of the generator. So you can see here this black disc, this outer black disc. This denotes the stator frame. The outer black disc denotes the stator frame. The stator frame is made of cast iron or cast steel. In small machines, the stator frame is made of cast iron because cast iron is cheaper. In large machines, it is made of cast steel because cast steel is lighter than cast iron. So while designing small machines, cost is the major factor. So cheaper material is used, and while designing large machines, weight is the major factor, so we use cast steel. The stator frame forms the outer covering of the machine. It is the outer covering of the machine. It is cylindrical in construction and it protects all the inner parts against any mechanical damages. And next to stator frame, in the inner periphery of the stator frame, this region is called as stator core. So the region inside the stator frame is called stator core. The stator core is made of some magnetic material like cast iron or cast steel. The stator core is having slots. to accommodate this stator winding. The stator core is fixed to the inner periphery of the stator frame. And next is the stator winding. We can able to see two coils in the stator windings. Those are connected in series. So the stator winding is made of insulated copper wire. When the magnetic flux linking with this winding changes, an EMF is induced in this winding. So these three parts together is called stator. Stator frame, stator core and stator winding. These three are stationary and it will not rotate. And next comes the rotor. This part is the rotor, rotating part of the machine. So this middle ring is called rotor core. It is made of heavy magnetic material. It is just an heavy magnetic wheel which is mounted on the shaft in this middle. And in this rotor core, two projected rotor poles are attached. Those are made of permanent magnet material like alnico. So one is the north pole and the other is the south pole. So the poles are projected outside the rotor core. The rotor is capable of rotation and it is driven in anti-clockwise direction. It is shown by arrow that it is driven in anti-clockwise direction. So rotor core and rotor poles are capable of rotation and hence it is called rotor. So first let me explain the operation of this AC generator. So it works based on Faraday's law of electromagnetic induction. When the magnetic flux which is linking with the stator coil changes, then voltage is produced or EMF is produced. And the produced EMF or the generated voltage will be sinusoidal. As shown here, the generated voltage is sinusoidal, whose maximum value will be Vm. And the value of induced EMF changes with the angle of rotation of the rotor. Now I am going to explain how this sinusoidal voltage is generated using this simple generator. Assume that the rotor is along the horizontal axis. Initially, the rotor is along the horizontal axis. So when the rotor is along the horizontal axis, when the rotor is along this horizontal axis, the coil at the top is neither under the influence of north pole nor under the influence of south pole. We are dealing with the coil which is at the top. The coil is neither under the influence of north pole nor under the influence of south pole. Hence, flux linkage is 0 and the induced EMF is 0. So, when the north pole and south pole lies along the horizontal axis, then the induced EMF in the coil is 0. When the rotor starts to rotate in anti-clockwise direction, first the north pole moves towards the coil which is at the top. The north pole moves towards the coil at the top. When the north pole starts to move towards the coil, flux linking with the coil starts to increase. When the flux linking with the coil increases, induced EMF will be also increasing, because based on Faraday's law, when a flux linking with the coil changes, EMF is induced and the magnitude of induced EMF is proportional to rate of change of flux. Now when the north pole is moving towards the coil, flux linking with the coil is changing, it is increasing. So an EMF is induced and the magnitude of induced EMF is also increasing along this sinusoidal curve. When the north pole comes exactly under the coil, induced EMF will be maximum because rate of change of flux will be maximum. So when the rotor makes 90-degree revolution, induced EMF is maximum. So in the sine curve at pi by 2 at 90-degree, induced EMF is maximum. Again, when the rotor is rotated in the anti-clockwise direction, the north pole moves away from the coil. When the north pole moves away from the coil, the magnetic flux linkage decreases. So there will be induced EMF, but the magnitude of induced EMF is decreasing. Since the flux linking with the coil is decreasing, magnitude of induced EMF is decreasing. Again, when the pole reaches the horizontal axis, the coil is not under the influence of south pole, neither under the influence of north pole. So flux linkage is 0 and induced EMF will be 0. So at 180-degree rotation of the pole, induced EMF is 0. In this waveform, at 180-degree at pi, induced EMF is 0. Now again, when the poles are rotated in anti-clockwise direction, the south pole starts to move towards the coil at the top. The south pole starts to approach the coil at the top. So flux linking with the coil will be increasing. Since the opposite pole comes near the coil, induced EMF will be in opposite direction. So induced EMF starts to increase in the negative side. When the south pole comes exactly under the coil, induced EMF will be maximum but in the negative direction. When the south pole moves away from the coil, induced EMF decreases but also in the negative direction. When this rotor completes one full rotation, that is 360-degree of rotation, it comes to initial position. So induced EMF will become 0 at 2 pi or 360-degree. So in this way, an sinusoidal voltage will be developed. Now I am going to demonstrate how this sinusoidal voltage is demonstrated using an animation video. So listen to this video. The same machine. Now the north pole and south pole of the rotor is along the horizontal axis. North pole and south pole of the rotor is along the horizontal axis. So we are dealing with the coil which is at the top. No flux links with the coil at the top. The coil is neither under the influence of north pole nor under the influence of south pole. So induced EMF is 0. This red ball shows the induced EMF. So induced EMF is now 0. And when this north pole, when this rotor is rotated in anti-clockwise direction, the north pole moves towards the coil. When the north pole moves towards the coil, flux linking with the coil will increase. So this red ball will starts to increase. Induced EMF will starts to increase. When the north pole comes exactly under the coil, flux linkage is maximum. So induced EMF will be maximum. So at 90-degree rotation of the rotor in anti-clockwise direction, induced EMF become maximum. Maximum at 90-degree. Again, when the north pole is rotated, the north pole will go away from the coil. So induced EMF will be decreasing. From maximum it will be decreasing and reaches 0 at 180 degree of rotation. Again, when it is rotated in anti-clockwise direction, south pole will move near to the coil. So when the coil is under the influence of south pole, same thing happens, but the induced EMF will be in the opposite direction. So just look at this animation video. So when the rotor is rotated, see what happens to this red bulb, what happens to this induced EMF, how it varies. So when the north pole moves towards the coil, induced EMF is increasing, reaching maximum at 90 degree, once again becoming 0. When it is under the influence of, when the top coil is under the influence of south pole, induced EMF is negative. Is it clear? The north pole moves, induced EMF is increasing. Okay, so when this rotor completes one full revolution, that is when the rotor completes 360 degree of the revolution, one north pole and one south pole cuts the coil. The coil comes under the influence of one north pole and south pole when the rotor completes one full revolution. So when the rotor completes one full revolution, one full cycle of alternating voltage is produced. When the coil is under the influence of north pole, positive half cycle is produced. When the coil is under the influence of south pole, negative half cycle is produced. So when the rotor completes one full rotation, one full cycle of AC is produced. I repeat, since there are two poles in the rotor, one north pole and south pole, when the rotor completes one full revolution, that is 360 degree of rotation, this coil comes under the influence of one north pole and one south pole. When the coil is under the influence of north pole, positive half cycle is generated, and when the coil is coming under the influence of south pole, and negative half cycle is generated. So full cycle of AC is generated. If suppose instead of two poles, if the rotor has four poles, what will happen? Two north pole and two south pole. When the coil completes one full revolution, when the rotor completes one full revolution, the coil comes under the influence of two north pole and two south pole. So in the picture I have shown only two magnetic poles. If instead of two poles, if you have four poles, when the rotor completes one full revolution, the coil comes under the influence of two north pole and two south pole. So when the rotor makes 360 degree revolution, the coil comes under the influence of two north pole and two south pole. So two cycles of AC waveform is generated. When the coil comes under the influence of first north pole and first south pole, one cycle. When the coil comes under the influence of second north pole and second south pole, second cycle. So the actual rotation of the rotor is denoted as mechanical angle, and the angle denoted in this waveform is called as electrical angle. Mechanical angle denoted as theta m, electrical angle denoted as theta e. So when the rotor has two poles, when it completes 360 degree rotation, waveform generated is 360 degree. So theta m equal to theta e. When it has four poles, when the rotor completes 360 degree revolution, here two cycles are generated, that is 720 degree generated. So electrical angle equal to 2 times mechanical angle. So just we can see that when the rotor has one pair of pole, that is one north pole and one south pole. When the rotor completes one full revolution, 360-degree revolution, one cycle of AC is generated. So electrical angle in the waveform is 360-degree and mechanical rotation theta m of the rotor is also 360-degree. So theta m equal to theta e. So in the second case, there are 2 north pole and 2 south pole in the rotor. It is a 4-pole machine. 2 north pole and 2 south pole. When the rotor completes 360-degree rotation, the coil comes under the influence of 2 pair of poles, 2 north pole and 2 south pole. So 2 full cycles of AC is generated. That means in the waveform 720 degree is generated, but in mechanical rotation only 360 degree, one full rotation. So when the rotor makes one full rotation, theta m equal to 360 degree, 2 cycles of waveforms are generated. So theta e equal to 720 degree. So we can write theta e equal to 2 into theta m. So we can generalize the case. If the machine is an p-pole machine, that is number of poles equal to p. P may be 4, 8, 16 or anything. So if the number of poles is p, then number of pole pair is p by 2. Okay, so theta electrical will be number of pole pair into theta m. So look at the first case. How many pole pairs are there? Pole pair is 1. So theta m equal to theta e. Look at the second case. How many pole pairs are there? 2 pair of poles. So theta m equal to 2 theta m. If you have p by 2 pair of poles, theta e equal to p by 2 into theta m. Clear? Next we can see the vector concept. Vector representation of a sine wave. So the generated voltage is a sine wave. This can be rotated. This can be represented as a rotating vector. So based on mathematical principles, any sinusoidal voltage with maximum value Vm, here the maximum value is Vm. Any sinusoidal voltage with the maximum value Vm can be represented as a vector. This red line indicates vector. Can be represented as a vector. And the magnitude of the vector is equal to maximum value. This magnitude of the vector is equal to maximum value, Vm. The vector rotates in anti-clockwise direction. And the component of the vector along the positive y-axis gives the value of voltage. So component of this voltage along y-axis is Vm sin theta. And the component along x-axis is Vm cos theta. So component along y-axis is Vm sin theta. So at any instant, if you substitute the value of theta, you will be getting the actual voltage, that is Vm sin theta. So any sinusoidal voltage with maximum value Vm can be represented as a vector whose magnitude equal to the maximum value Vm, and the vector rotates in anti-clockwise direction, and the component of the vector along y-axis gives the value of voltage at any instant of time. So just imagine the rotation of the rotor. In the previous simulation, I have shown that the rotor is rotating. The rotor is also rotating in anti-clockwise direction. Instead of that, and vector with maximum value Vm is rotating in anti-clockwise direction in coinciding with the speed of the rotor. And the generated waveform is Vm sin theta. So at any value of theta, the y-axis component gives the value of voltage. So thank you. Bye bye.